Great, thank you so much. Hi everyone, I hope you're doing well. My name is Mabel Atiyeh and I'll be presenting today an overview of transfer learning. So a little bit about myself. I'm a senior computer engineering student with pre-med track at the Lebanese American University in Lebanon. And mainly what I do is that I pursue both computer engineering and pre-med, so medicine. I'm also interested later on in pursuing a master's degree, either in biomedical engineering or most probably in computational neuroscience. And mainly my focus is on biology and medicine. Now, today I'll be covering briefly transfer learning. Then we'll also dive into an example on Google Colab, so stay tuned. And I can assure you, once I finish presenting, you will have all of the basics needed to dive deeper into this really interesting topic. Now, for the questions, we'll keep them till the end. So if you have any questions and we did not have time to answer them or anything at all, you can also always refer to Hassan and Sarah. Now, let's talk more about transfer learning. Let's start with it and let's see what we'll learn today. Imagine you've learned how to ride a bicycle. You've mastered balance, learned how to steer, brake, and maybe adjust your posture. One day, you try riding a motorcycle. Although it's two different vehicles, however, many of the foundational skills transfer. So let's say balancing on two wheels, coordinating your hands and feet, looking ahead to steer, maybe staying upright at different speeds. You don't need to start from zero. You just transfer your knowledge from cycling to motorcycling. And this is the essence of transfer learning. In machine learning, the idea that knowledge gained while solving one problem can be reused to solve a different but also very related problem, that's just transfer learning. So just like human beings don't start from scratch every time they face a new challenge, machine learning models can also benefit from previously learned experiences. So in technical terms, transfer learning is a technique in machine learning where a model trained on one task is repurposed, either in full or in part, we'll talk about that later on, for a second but related task. So it should be related. And the key idea is to transfer the knowledge learned by a model on a source domain, and we have to transfer it from the source domain to another target domain. So the components that we will be talking about mainly today are the source domain, which is the domain where the model is initially trained, the target domain, the domain where the model is to be applied. So let's say medical imaging. We also have source task, which is the task that the model is originally trained on, and the target task, the task that we want the model to be used on. Now, let's see why we use transfer learning. A very fun example I always like to use, which is the rice example. So imagine you're hungry and you want to cook a meal. Instead of cooking everything from raw ingredients, you use pre-cooked rice. This saves time and energy. You just need to add spices, vegetables, and I don't know, maybe you like some proteins, but your meal will be ready in minutes instead of hours. Similarly, in machine learning, instead of training a model from scratch, which can take days or sometimes even weeks, like it depends on the data, you start with a pre-trained model. This model, it already knows how to detect edges, shapes, textures, maybe other visual patterns. And you can also think about it from different perspective, like different analogies. Maybe in Legos, you don't have to build every block from atoms. You just use pre-shaped pieces. So the pieces are already there, you're just using them. Or maybe learning new languages. If you already know Spanish, then Italian is going to become way easier because there are so many similarities in vocabulary and in grammar. So transfer learning, it reduces time, computation. It also has like less data requirements, which makes it highly, highly practical. Now, if you want to take it onto the technical side, so from a technical perspective, transfer learning is really good because it reduces training time. So you are using a pre-trained model, which speeds up development. It requires less data. So it's useful when the target task has limited data. It also improves generalization because pre-trained models capture robust features. We can also talk about performance because it boosts performance often yields better results on small data sets, which is really useful again. And we'll see why in other animations on other slides. And finally, it enables rapid prototyping, so you can do quicker iterations and experimentation. And this is especially important in domains like medicine or sometimes space science, where data is really expensive and scarce. Now, how does it work? We have spoken about its benefits, we have talked about what transfer learning is in general, but what really matters is how it works. So let's see it together. So we have three main stages. Pre-training model is trained on a very large scale data set. So we have, for example, ImageNet. It has like over 14 million images, and the model then it learns low-level features. When I talk about low-level features, I mean edges, shapes, and it also learns mid-level features like object parts and high-level features like the entire object. And usually we use in this part models like ResNet, Inception. If it's text, you can also use BERT. The second stage, it's transfer, it's initialization. So as we have spoken, like in the earlier stage, the model has learned the features. Now, the pre-trained model, it's going to be taken as a starting point. The base layers are reused, and then the final layers, you can either replace them or extend them. And this is where knowledge is transferred. Our third and last step is going to be the fine-tuning. Fine-tuning, it's when the model is trained further on the new data set. And this can involve training only the new layers, or maybe updating all layers with a small learning rate. And the goal from this step is to adapt the pre-trained features to the new domain. And like all of these steps are really important, and they allow flexibility, but it depends also on the size of the data set that you are using and how different the new task is from the original one. Now, why it's useful in many domains, especially medical imaging. So medical imaging is one of the most important areas for transfer learning, and let's see why. First, we have a lot of data scarcity because medical images are really difficult to obtain due to privacy, due to cost, sometimes due to the need of expert labeling. We also have another problem, which is the expert knowledge required, because labeling X-rays, MRI, CT scans, they require intelligence or really special in the field, which makes it like really harder. We have also the high accuracy demand, because as you can see in many cases these days, if you misclassify something, it can lead to serious consequences, especially in the medical field. We also have visual similarity. Features, images, textures, shapes, they are useful in medical imaging, and they are very similar. So some examples, we move on. We have like tumor classification. We can use transfer learning classify certain tumors from MRI. There's retinal analysis. There's melanoma detection. And transfer learning reduces the reliance on massive data sets while also achieving high accuracy and reliability. Now let's talk about the types of transfer learning. As you can clearly see, there are three types. We're going to start with the feature extraction. So in the feature extraction, mainly you're going to use the convolutional base, which is the feature extractor of a pre-trained model. You freeze all of the layers, and you add new layers on top, tailored for the new task. Only the new layers are trained. What are the pros or the cons? Let's check each one for each type. So for the feature extraction, the pros are that it's going to have a faster training. It also avoids overfitting on small data sets. However, we have cons, which is that it's less adaptable to new domains. The second type is fine-tuning. So in fine-tuning, you're going to unfreeze some or all of the layers of the pre-trained model, and you're going to retrain the model on the new data set with a small learning rate. That allows the model to adapt to new data nuances. So what are the pros and what are the cons? The pros have a better performance on domain-specific tasks, and the cons is that it's going to require a lot more data and higher computational cost. So it's going to cost more when we're talking about computation. Now the third and final type, which is the partial fine-tuning. In this step, we're going to freeze the lower early layers. So the early layers, we freeze them. However, the higher and later layers, we're going to unfreeze them. And then we're going to fine-tune only a portion of the model. And why do that? Why are we freezing the lower early layers and unfreezing higher later layers? The early layers, they learn general patterns like edges, touches. However, late layers are more task-specific. As for precise data sets, or when the new task is somewhat related to the original one. Now, let's see a bit the performance observations. So, studies and real-world applications have shown that the transfer can outcome the medium-sized data sets. Also, we have discovered that pre-trained models, so models such as ResNet, Inception, EfficientNet, they have demonstrated excellent transferability. Also, transferring, it helps avoid overfitting, like I have mentioned earlier, because it starts with weights that are being well regularized. However, for very different domains, so using natural image features for MRI scans, scan is like dropout, proper fine-tuning. So the metrics that you have to always consider and make sure that are there are accuracy, precision, recall, training time, the robustness of the model, that type of stuff. Now we will talk about machine learning. We will be taking an example. So together. So mainly we have a certain model that's trained on millions of cats and dogs. So let's say we're taking ImageNet. Okay? So it's trained on ImageNet and it already knows how to detect patterns and in images. So first we're going to go through steps, like what steps you have to take. So first, you're going to load the pre-trained model, so the pre-trained ResNet, and then you have to remove the final classification layer. So let's say that it already outputs a different class. You have to replace it with a new output layer. So no classification. Then the third step is that you need to freeze most layers. So you keep the base weights unchanged, and only layers are trainable. Then you're going to train it on chest X-ray dataset. So you fine-tune the model using your dataset. You use data augmentation to increase dataset variety, and then you're going to evaluate it, which we're going to do very soon. And during evaluation, you're going to monitor accuracy, you're going to monitor loss, and you're going to monitor other things. This way, your model will benefit from millions of seen images. Even if your data set it only contained like 2,000 X-rays, it's still going to work. So the model is going to use those previously seen images, and it's going to be able to output a really accurate result. So these results are going to be much more accurate than from scratch. It's going to have a faster conversion as well, and the performance overall it's also going to be more stable. This is going to be very useful for your dataset and for your work. Now a quick summary. So transfer learning, it's like I always use the example, it's like standing on the shoulders of giants. So you use this knowledge from existing model and you're able to train it faster to use less data, which is useful, especially as mentioned in the math field. And you are able to do a lot more, and your performance is way, way better. So it kind of mimics how humans learn, built on prior experience. Whether it's using pre-cooked rice or adapting from riding a bicycle to a motorcycle, the principle, it will always remain the same. And in fields like medical imaging, where data is scarce and stakes are really high, because in medicine you can't really make mistakes. It's going to cost the lives of many people. Transfer learning is just transformative. So my key takeaway before we take an example are always remember that transfer learning, it reuses knowledge from one task to another. It involves 3 steps, 3 stages. We have pre-training, transferring, fine-tuning. There are several strategies and types, like feature extraction, fine-tuning, partial fine-tuning. And it's always really useful, especially for high stakes, for low data environments, and fields such as medicine, space science. And how I would like to end this Canvas slide to finish it with this sentence, which is, as machine learning are going to advance, and they will advance a lot, transfer learning will become even a more crucial and core technique to achieve smarter, faster, and more efficient models. So now we'll be taking an example. Just give me a second. So we don't have an actual data set. We have created a function to simulate a data set used to simulate the workflow. And I'll be telling you about your challenge soon. But before that, go over this Google Colab code. So we will start by installing the necessary packages for our project. What are those packages? They include TensorFlow for building and training deep learning models. They also include Matplotlib for creating visualization. We also have Pillow for image processing. And once these packages are installed, our environment will be ready, and we will be able to use the transfer learning setup. Next, we will also import the essential libraries we will be using throughout the project. So as you can see here, we have imported TensorFlow, we have imported NumPy, Matplotlib, we have imported also scikit-learn, warnings. So let's go through each one of them to understand them more. So TensorFlow and Keras will handle deep learning tasks. NumPy will help us manage numerical data efficiently. Matplotlib is for visualization, and scikit-learn will help with data splitting. We also have used the warnings module, as you can see, and it's going to be really helpful to suppress unnecessary warnings and to keep our output clean. Then after we have imported those really important libraries, we will perform a quick environment check. So we have printed the versions of TensorFlow, of Python, of NumPy, Matplotlib to ensure compatibility. And lastly, we check that the GPU is available, because using a GPU, it speeds up training a lot more compared to a CPU. Then, now I've created a simple function, and it's called show medical applications. It's going to highlight where for learning is used in real-world medical scenarios. So let's see it together. This function categorizes applications based on medical fields. So like chest X-ray analysis, dermatology, neurology, pathology. You can check them here. The red text paragraphs, if you can see them here. Yeah, so for example, in chest X-ray, transfer learning is going to help with the pneumonia detection and COVID-19 screening. Similarly, in dermatology, it can classify skin cancer or even detect melanoma, which is super helpful. Now, after using the application, the function is also going to explain the key advantages of transfer learning in medicine. So it's going to require less data, which is really important because medical data sets are often small. It will speed up the training process by using pre-trains, and it's cost-effective and performs better on limited data. We then run the function to print all of this information in an easy-to-read format. So I'm going to run it again. And as you can see, it's all printed. The advantages, the reward medical applications that we have mentioned earlier. Now next, we are building our transfer learning model, and this transfer learning model is for medical image classification, right? So we use ResNet-50. It's a powerful deep learning neural network pre-trained on over 1.2 million images from ImageNet. So the beauty of transfer learning is that we don't need to train a model from scratch. We just, as we have mentioned earlier, reuse the feature extraction power of ResNet-50 and just add our customers on top. So here's the process. First, we will load the pre-trained ResNet-50 model, removing its original classification layer because our task is going to be different. So we have to remove the original classification layer. Then we're going to freeze all the pre-trained layers so they don't get updated during training. And this is where transfer learning works its magic. Then we're going to add our own classification head, which includes a global average pooling layer to convert 2D features into 1D, a couple of dropout layers to reduce overfitting. We also have a dance layer with 128 neurons for learning complex patterns. And finally, a softmax output layer to classify our medical images. Now, after building the model, we're going to compile it using the Adam optimizer and metrics like accuracy, precision, and other metrics. And always recall, these are really important for medical diagnosis. So once the model is ready, we print its summary, and we're going to be able to now see the architecture, the number of parameters, and which layers are trainable or frozen. So we printed them, I already ran it, so you can see now the results. Now, after creating our transfer learning model, we can see the architecture summary, right? So first layer is going to be ResNet-50, which acts as our powerful feature extractor. We then have a global average pooling layer to flatten the feature, followed by a dropout layer to prevent overfitting, a dance layer with 128 neurons, another dropout, then a dance layer with like other neurons as well, another dropout, and this is like overall a body classification path. Looking at the parameters, we have about 23.8 million parameters in total. And most of them, 23.5 million, are frozen and they are not trainable, while only 262,530 parameters from our custom heads will be trained. So this makes training much faster and more efficient. So we're only fine-tuning the final layers instead of the whole entire ResNet-50. So only we're training, like, it's way less. It's going to take less training time, less computation. It's really useful. Now, we're going to focus on preparing our data set. So as you can see, our function, it's now called pre-process medical images. And this function is going to ensure that all medical images are resized to 124 and pre-processed according to the ResNet-50 requirements. So if we have raw images, like the image files, and loaded, so they're going to be converted to arrays and normalized for a better performance. Now, since we don't have an actual medical data set here, we have created a synthetic data set with this function, which is create synthetic medical data set, so that we're able to see the transfer learning and how to use it. We have this function. Now, this function, what it's going to do, its benefits is that it's able to generate random images, balanced labels, just to demonstrate the workflow. Now, after creating our synthetic data, we pre-process it, we check its details. When I talk about details, I mean the image shape, the label shape, the classes, value range. Then finally, we split the data into training and testing set, which helps maintain class balance and be crucial for medical applications. Now we're going to begin training our medical transfer learning model. So for this demo, we train for 5 epochs with a batch size of 16 using the Adam optimizer and using also a learning rate, which is 0.001. We have set up 2 callbacks. We have early stopping, which holds if the model stops improving. And we also have learning rate reduction, which fine-tunes the learning rate for better conversions. Now, after training, we evaluate the model here, this part, we're here, in case you're confused. So we're evaluating the final model, and we evaluate it on the test set and measure performance using key metrics. So when I say key metrics, I mean accuracy, precision, recall, and the F1 score. These metrics are really important and critical in medical applications because we care not only about how often the model is correct, but we also need to care about minimizing false negatives and false positives. So it's really important to pay attention to these two the results. The training process is complete. Already ran it earlier to save time. And the logs, as you can see here, these are the logs. So after the training time. And the final evaluation of the content, which is really important and meaningful. And this number, it means that the model is correct slightly more than half of the time, which is now the and equal are both around 52%, which shows the balance in correctly predicted positives. So in case the model says it's positive but it's not, so it's going with that. And finally, we have here the F1 score. That's the model performance summary here. That is the final model evaluation. So the F1 score is the mean, precision, and recall. And it's in this case around 0.52. And you have to keep in mind that this performance is on a synthetic data set. So medical data and proper fine-tuning, of course, expect much better. But as a first step, this really now that our training is complete, let us visualize how the model perform during each epoch. So we use the plot training history, so this function now, just so that you can see it. So we're going over this function. All right. So this function here is going to help us a lot. Why? Because now that our training is complete, we have to visualize how the model performed during each epoch. So we use the plot training history function to create 4 key charts. First, accuracy. So accuracy, I have mentioned a lot earlier. However, let's talk about what it actually means. Accuracy, it shows how well the model correctly classifies during training versus during validation, which is really important, especially in the medical field and in other fields as well. Second, going to talk about the loss, which is a metric that measures how far our predictions are from the correct labels. And ideally, loss should decrease over time. It should not increase. It should decrease. It should go lower. We have our third metric, which is precision, is going to tell us how many of the model positive predictions were correct. And finally, we have the recall to show how many actual positive cases we have successfully identified. So to go over the code, here it's the accuracy plot. We're going to see the plot later on. This is the part of accuracy. This one is going to plot the loss which measures how far our predictions are from the correct labels. And as we have said earlier, we should expect a decrease over time. Here we have the precision plot, which will tell us how many of the model's positive predictions were correct. And the fourth criteria, which is the recall, which is going to show how many actual positive cases have successfully identified. Now the summary is then going to be printed, and validation, accuracy, and loss after the last training. And we also are going to check for something really important, is overfitting. Now, we will check for overfitting in this part. So overfitting, what is it exactly? Overfitting is something that happens when the model performs well on training data, but poorly on validation data. So I'm going to repeat it because it might be a bit complicated. So overfitting, it happens when our model is doing well on the training data. However, when we're working on validation data, it's performing poorly. So how are we going to test that? We have here the if function, and the function is comparing the result with 0.1 with 0.05. So let's talk more about that. So if the accuracy gap between the training and validation is too hard, we might add techniques like data augmentation, the dropout layers, you can add regularization. So in short, these plots and maps give us a clear picture of how well the model is learning and generalizing. Now let's talk about our results. So as you can see, we have 4 graphs. We're going to go over each graph alone, but before that, here you can check the training summary. And this one, it clearly identifies the charts that are displayed above. So these are just to make our lives a bit easier. Now we will go over each chart alone. First, we have our top one. This one, model accuracy. So the training and validation accuracy, they clearly stay close to each other, which suggests that our model isn't overfitting heavily. So look at the data. You can see that it's around the same, like very close values. They are not different, which is good. Now, if we look at the top right, the model loss, we can see a steady decrease in training loss. And this one, the blue line, it's decreasing. And the validation, the orange line, it fluctuates slightly. And this is very common. This is normal because we're working with small data sets. So you can expect that result. Now, if we check the model precision, we have the results, they are hovering around 0.5. Look, here's the 0.4. This one is 0.6. So the results are around here, around the 0.5. So what does that mean? We now about model precision. So that means that half of the positive predictions they're correct. So 50% of our predictions are correct. Now, if you go to the model recall, so bottom right, this one, it also remains around 0.5. Look, this is 0.4, this is 0.5. If you check the training recall, the purple line, it's around 0.5. The validation recall as well. Both of them are really close to each other, just like the model precision. And it's important to understand that since recall also remains around 0.5, then the model catches about half of all actual positive cases. Why are these graphs useful? What do they tell us? Why did we go over them? Before I tell you the answer, let's check quickly the training summary and let's go over the charts. Even though we already went over them, however, it's really important to recover them. So the summary, we have the final training accuracy, as you have seen above, it's around 0.5. Final validation accuracy, around 0.52. The final training loss, it's 0.92. The final validation loss is 0.71. So overall, have a good generalization, have low overfitting. And in case you forgot what overfitting means, this happens when the model performs well on training data, but it performs poorly on validation data. So now let's have a quick summary about all of these graphs that I've seen earlier. So these graphs that while the model is learning, its performance is limited by the synthetic data. So with real medical data sets, of course, these metrics are going to improve way more. So this precision is not ideal. However, it can be way, way higher. But we're now working with synthetic data sets. So in case we work with real medical data, then everything would improve significantly. This is mainly it regarding the code. Now you might be thinking, why did we cover this whole code and the Google Colab? However, the data set was all synthetic. How are we going to see the actual real data set and the actual real results? This is where our challenge comes. So we challenge each and every single one of you to now take the initiative and to work on an actual data set, any medical data set, you choose it, and you have to apply this workflow on it. And we're going to check the best results and work, and the best results are going to be rewarded. So take this challenge and make sure to use, as I mentioned, real data sets, real medical data sets, and see the results. They should be improving way more. So these graphs are going to be totally different, and you're going to see a lot more improvement when using real data sets. So this is it for my presentation. If anyone has any questions, any concerns, anything at all, feel free to let us know. I hope you have benefited from the Google Colab and from the overall PowerPoint presentation. Yeah, thank you so much. As I have mentioned, we have the challenge and questions. So I'll repeat the challenge. The challenge is that now that we have went over the code, we have used the synthetic data sets. However, we need you to do a medical data set. So use a real-world medical data set, and we want you to show us the results, and the best work is going to be rewarded. So make sure to do that, and we're waiting for you. If you have any questions, please please also let us know. Also, regarding the challenge, as I have mentioned earlier, I'm going to repeat it one more time. You need to use a real medical data set and to try it out. I'm sorry about that. Yeah, so you're going to use a real data set and make sure to finish it by tomorrow at 7 p.m. And make sure also to tag Sarah in the LinkedIn post, or you can tag me as well. You have until tomorrow at 7 p.m. So make sure to finish it. It's going to be a really fun challenge, and we can't wait to see your results. So that's it from my part. I hope you have benefited from it. And thank you so much for listening. I hope you also dive deeper into transfer learning. It's a really amazing and beneficial concept. And I would like to thank you again so much for listening to me. And we would love to see you tag us. And that's it. Have an amazing day and enjoy the session after me. It's going to be very beneficial. And yeah.
it's clear, or I have to just do something before starting? Okay, just please start streaming right now. It's clear, or I have. Okay. So, hello everyone, and welcome to this session where we are going, but first of all, is everything is clear? Okay, so that's not problem. First of all, hello everyone, and welcome to this session where we are going to discuss together how we can build an AI model to predict whether the email is a phishing email or is a legitimate email. So starting by this image, there are some steps that we are going to talk about in this session. And in order to understand all of them, let me just introduce these steps. So first of all, starting by importing some libraries, like pandas, numpy, scipy, and many others, okay, that we are going to use them later. And then, as you know, it's an AI model, okay? Okay, my voice is low. So as you know, this is an AI model. So we have to just download a data set where we can train and test our model, okay? So in this purpose, I just downloaded a data from Kaggle, okay? This data is just like this. Each row represents a separated email, which contains a sender, receiver, the date, the subject, and the body of the email. And in addition to all of those, there is a label column, which just holds even one of the two values, even 1 or 0. So if the label is 1, we can identify that this email is a phishing email. Whereas if the label is 0, like here, let me just scroll down. If the label is 0, just like this one, this represents that this email in this row is a legitimate email, okay? So after downloading the data, we have to make sure that there is no null values. In order to do that, we have just to say, okay, this data is not our data, so we don't know its content. But we have to say that, okay, the subject, keep it as it is, but if the value is null, just replace null with an empty string, for example. And the same applied for body, okay? Because later on we are going to concatenate subject and body, and if one of them is null, this could cause a problem. So let's just continue. After cleaning the data and the missing values, we have to just look at the importance of each word, okay? And we have to ignore some words like of, the stop words in English, like of, your, at, and many others. And this is called the TF-IDF technique, okay? So like that, we are going just to take some vocabularies from the email and look at their importance level. And after doing that, we have to split our data into two sets, okay? Just let's take a small example to make everything clear. If we have 100 email in our main Kaggle data set, we are going to split this data into two separated data sets. The first one composed of 80%, which is an 80 email, okay, of the main data set, and the rest 20% of the 100% goes to testing purposes. So this data set, we will be used to train our model, and this after training our model, we are going to test it using this 20% of our data, And just after splitting our data, okay, into training and testing purposes, okay, we have to start training our model. So we are going to take this 80% of the data frame and just train our model based into them. And after training, just start by making some predictions. From what? From this test data set. Okay? And the model will predict whether each email in this 20% data set is a phishing email or is a legitimate email. And after that, we have the labels, but the model don't know anything or doesn't know anything about them. Okay? So we are going to compare the predictions with the correct labels. And we are going to evaluate the model accuracy. Okay? So after doing all of these steps, we are going to write our own email and try to provide it to our model and just look at if the model can identify whether it's an phishing email or not. So this is our main session today. This is our main steps that we are going to walk through in this session. So as I said, we are going to import some libraries like NumPy, Pandas, and many others. Okay, so I recently talked about the data that I downloaded from Kaggle. Okay, let me just speak this one more time. Each row represent an email. Okay, the email contains a subject, a body, and a label. Okay, the label can hold either 1 or 0. If the label is 0, so the email in this row is a legitimate email. Whereas if the label is 1, like here, then this email in this row is a phishing email. Is everything clear? I hope that everything is clear till now. Okay, so let me just open the comment. Okay, so if there is anything you would like to ask about, just leave a comment. Okay, so let's continue. By taking an example, okay, we have two emails, the first email and the second email. I would like just to give you some time to read both of these emails, okay, but I will make sure that everything is going. Okay. So, for example, we have the first email and we have the second email. The first email subject is "Hi team." The body of the first email, just a quick reminder about tomorrow's meeting at 10 a.m. in conference room B. Let me know if you need to reschedule. Best regards, Abbas. So, as you can see, there is nothing suspicious in this email. Okay, let's go and see the next email. Email number 2 subject. Action required. Your account will be suspended. Dear customer, we detected suspicious activity in your account. Please log in immediately to verify your identity. http fakebanklogin.com verify. Failure to do so within 24 hours will result in account suspension. Can you just detect which one is the phishing email and which one is the legitimate email? Okay, as a humans, we can just directly identify that the first one is the legitimate email and the second one is the phishing email. Okay, but based on what? Based on some vocabularies that we read. Okay, like for example, if we look at the second email, action required. This is a suspicion, okay? Not suspicious, not a usual word, okay? So, your account will be suspended, okay? Suspended. Also a suspicious word. Dear customer, we detected suspicious activities. Look at how many vocabularies we have. In your account, please log in immediately They are pushing us to do something, to verify your identity. And there is a link right here. Okay, and it's HTTP without the secure layer. Okay, and there is unfamiliar, there is unusual link right here. Okay, so and failure to do so within 24 hours will result in account suspension. That's unusual in the emails. So we can identify that this email is the phishing email and the first email is the legitimate email, because there are no vocabularies in the first email that we can detect from them that the first email is the phishing email. So the first one is the legitimate and the second one is the phishing. Okay, but how the model can work with them? How the model can identify and know which one of those is the phishing and which one is the legitimate? So the model are going to ignore some words, the stop words in English, okay? Like hi, team, for example, just about, let's say that at also, and many others. In the second email, the stop words are, for example, well, and you, and for example, and many others like to, your, and many others. Okay? So the model are going to ignore many stop words. Okay? So, and then after that, we are going to create a table, okay, consists of many columns. The first column is the term, which is the vocabulary that the model picked up from the emails. For example, the model took the meeting vocabulary or meeting term, which is right here. We can find meeting right here. Reminder, where is the reminder? Okay, reminder, reschedule. Here, as you can see, this is the first term, this is the second term, this is the third one. Account, account is here in the second email, okay? Verify, verify is also in the second email. Login, where is login? Here is login. HTTP, in the link in the second email. Identity, identity is also in the second email. Okay. What about your and if and to? Those are stop words, but I added them just to say that we can add some words from our choice, okay? Like I left your and if and to. For example, your is found right here. Where is your, where is your, here is your, okay? If, you can just see if right here, and also a to. So, what about just a quick and tomorrow's and conference? We ignored all of them, okay? And we just focused on what really mattered, okay? So after this column, let's move to the next column, which is the TF. But let me just, okay, make everything clear. Okay, we just finished the first term column. Let's move to the next column, which is the TF, which is the TF of email number 1. Okay, just focus. A TF, term frequency of email number 1. And then we are going to calculate the TF, okay, of email number 2. So we will start by email number 1. But first of all, what's the term frequency TF? What its rule and how we can calculate it? First, let's go and read this definition of TF-IDF. TF-IDF stands for term frequency inverse document frequency. It's a statistical measure used in natural language processing, NLP, and information retrieval to evaluate the importance of a word in a document relative to a collection of documents purpose. Okay? So, TF-IDF is responsible just to identify the importance or to evaluate the importance of each word in our document. Okay? This is the TF-IDF. Okay, let's calculate first of all TF, and then we are going to calculate the IDF. Then, after that, we will calculate the TF-IDF together. But as you can see right here, I just wrote the role of the TF. Okay, let's just scale it up a bit. Okay, so the TF takes two arguments. The first one is the term, the second one is the document that we are working with. For example, what does that mean? Let's take a look right here. As I said, in this column, we are calculating the TF of email 1. So the document is email 1. First row is the term meeting. So we are calculating the TF of the term meeting in the document email 1. Okay, so let's see what's the role is. Okay, the role is that TF of term TD. Okay, so T here is meeting. Okay, and the document right here is the email number 1, SE1. Okay, so what's the rule? It's the number of times term T appears in document D. So how many times the term meeting appears in email 1? Let's just count them. How many times term meeting appears in email 1? Okay. Hi team, just a quick reminder. Okay, hi team, just a quick reminder about tomorrow's meeting. Okay, this is, for now, it existed only one time. Okay, we found it. At 10 a.m. in conference room B, let me know if you need to reschedule. Best regards, Abbas. So we found the term meeting only one time in the first email. So the numerator are going to be 1. Okay, the numerator is 1. Okay, but what's about the denominator? The denominator is the total number of terms in the document. The document here, don't forget, it's the first email, email number 1. So the total number of terms in email number 1, let's just count them. Okay, so let's count. 1, okay, let me take a pen and clear. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27, okay, terms in the first email. So the denominator is which is the total number of terms in email 1. We count them and we found that the number of terms is 27. So the final result of TF of term meeting and document E1 is 1 over 27. Is that correct? We can just look at it right here. The TF of term meeting, okay, and email 1 is 1 over 27 of term reminder in email number 1. The TF of term reschedule in email number 1, and so on. Okay, this is how we can calculate the TF. And the same applied for email number 2. In email number 2, we are going to just do the same steps. We are going to use the same rule, okay? But we are going to use the second email instead of the first one, okay? So we are going to count. Let's just go back to the rule, okay? The rule is, okay, now we are dealing with email number 2, okay? With email number 2. Is that right? So because of that, we are going to count the number of times term T appears in document. What's the document in our case right here? The document email 2, okay? So the number of times term meeting appears in document email 2, we can just look at email number 2. There is no any appearance of term meeting in email number 2, the second email. So because of that, the numerator will be 0, as you can see. Okay, the numerator is what? Is 0. Okay, the denominator is the number of terms in email number 2, which is 38 terms. Okay, so 0 over 38, which is 0. So we'll apply the same steps for the rest of the terms. Okay. Okay, moving to the next step. Calculating the TF, after calculating the TF of each term, okay, in every document, we are going just to calculate the DFT. Okay, DFT is the document frequency. It's the number of documents in the corpus that contain a specific term. Okay, number of documents that contains this term. Okay, for example, let's go back. Okay, what's the document frequency of the term meeting? We have to look at every document, at each document, and see if this term exists in that document. For example, we can see that term meeting. We can just take it from the emails right here. Term meeting appears in the first email. Is that right? Here it is. Okay. And it also doesn't appear in the second one. So, in how many documents the term meeting appears? Okay, it appears in only one document. So the DF document frequency is only one. Okay. However, if we look at your, okay, term your, okay, the term your just exist in the first and the second email. Here we can find the term your in the second email, and here, okay, and here we can find the term your in the first email. Where is your, okay, blah blah blah. Okay, I think this should be your. Okay, so it appears in two documents. Okay, one in the first document and one in the second document. So it appears in two documents. So the DFT is 2. Okay, moving to the next column, which is the IDF. The role of the IDF is look based on. Let me just clear to make everything obvious to you. Okay, so the IDF is the look based on of N over DFT. DFT, we calculated that. We recently calculated the DFT of each term. Is that right? So, what's the capital N? Is the number of documents that we have. We have email 1 and we have email 2. So, how many documents we have? We have 2 documents. So, the capital N is always equal to what? Is equal to 2. Okay? So, look based on of 2 over DFT. Let's just move now. Calculate the IDF. So, what's the ITF? What's the IDF? Inverse document frequency of term meeting. Of term meeting. What's the IDF of term meeting? It's look based on of 2 over DFT of term meeting. So, look based on of 2 over the DFT of term meeting is 1. So, look based on of 2 over 1 is 0.3010. Okay? The same applied here. Okay. عم بسمع صوتك كثير واضح. حاول ابعت مسج إذا بتحب على الكومنتس. Yes, okay. Okay, so are you live right now? حسن انت هلا عامل ستريمينج ولا بعد disconnected? We are good to go. Okay. So sorry for the interruption. Okay. So let's continue from where we left in the last second. So, as I said, how we can calculate the IDF right now. To calculate the IDF, there is a rule that we have to walk through it. Okay? So, the IDF of a specific term, okay? The IDF of a specific term is the log-based ton of the number of documents we have over the DFT, okay? Okay, so what is the DFT? DFT, we calculated it recently right here, as you can see. This is the DFT, okay? The DFT of term meeting is 1. The DFT of term reminder is also 1. The DFT of term account is also 1, and so on, okay? So, how many documents we have? We have email 1, the document email 1, and we have the document email 2. So in total we have 2 documents. So the capital N, which is the number of documents that we have, is always equal to 2. Okay? So the IDF of a specific term is the log-based N of the number of documents we have over the DFT of this term. Okay? So it's always equal to log-based N of 2 over DFT. Okay? Because N is always equal to 2 because we have 2 documents, E1 and E2. So what's now? Now we are going to calculate the IDF of the first term, which is term meeting. Okay? What's the IDF of term meeting? The IDF of term meeting, okay, is log-based N, is log-based N of capital N, which is the number of documents we have, and we have only 2 documents, okay? So, of 2 over DFT of this term. So, we are calculating the IDF of term meeting. So, what's the DFT of this term? The DFT of this term is 1, as you can see right here, okay? So, it's log-based N of 2 over 1, okay? The result is, as you can see right here, 0.3010, okay? The same applied for the rest terms, okay? So also we can calculate the IDF, for example, of term HTTP, okay? The IDF of HTTP term is log-based N of 2 over the IDT of term HTTP. This is the HTTP term. The IDT is also 1. So log-based N of 2 over 1, which is also 0.3010. Okay? This is how we can calculate the IDF of the terms. Moving to the next column. We finished calculating the IDF. So what's next? After calculating the TF of each email and calculating the IDF, now we can calculate the TF IDF. Okay? We can calculate the TF and IDF. So, what's the rule right here? Sorry. Okay. So, what's the rule? It's the TF IDF, IDF is equal to the IDF itself times the TF. And as we know, we have TF for email number 1, as you can see in the second column, and TF of email number 2. Okay? So, we are going to calculate TF IDF for each one of the 2 emails. Okay? So, the TF IDF of email number 1 is the IDF times TF of email number 1. So, of term meeting, what's the IDF right here? It's 0.3010. And what's the TF of email number 1? It's 0.0370. Okay? So, the final result is 0.0370 times 0.3010. So, 0.0111 is the final answer. Okay? And we do the same steps for all of the terms, or for the rest terms. Now, after calculating the TF-IDF of email number 1, okay, after calculating the TF-IDF of email number 1, now we can calculate the TF-IDF of email number 2, and within the same steps as we did recently, okay, we can just take the TF, okay, we can just take the TF of email number 2 right here. Let's look up there, okay. We can take F of email number 2 is in this column, as you can see, okay. Okay, so, and here is the IDF. So multiplying the first row here and the first value here, we have of email number 1, which is for term meeting, okay. So for the TF-IDF of term meeting, we can just take the IDF, which is the 0.3010, and multiply it by the TF of this term, which is the meeting term, 0.000, and so on. So the result is 0, as you can see right here. Let's move to the next row. How we can calculate the TF-IDF of email 2 based on the term reminder. Based on the term reminder, to calculate the TF-IDF, we are going to take the IDF of this term, which we are going to take the IDF of this term, which is 0.3010, 0. And multiply it. We can just go by using them alone. We can just go by using them alone. But what's better is to use some special features. Okay? Like as humans, we can just say that the number of links in the email, some suspicious words like verify, PayPal, account, verify, and many others can be unusual. Okay? So we can rely only on these vocabularies or on the model, because the model is the one that chooses the terms right here. However, if we want to add new features, we can just add them, as you can see here. In addition to all of the above vocabularies, we can add, for example, the number of or not. Okay? Let me check something. So, okay, so the number of links in the first email. What's the number of links in the first email? Let's check out together. Is there any link in the first email? The answer is no. Okay, there are 0 links in the first email, so we put 0. What's the number of links in the second email? Let's go and see. The number of links in the second email is 1, http fakebanklogin.com/verify. So the number of links is 1 in the second email. Okay, moving to the next special feature. Okay, let's see clear. What's the next special feature? The next special feature that we added is the suspicious words. How many suspicious words are found in email number 1, and how many suspicious words are there in email number 2? Okay, what are the suspicious words that we are going to search about? The suspicious words, we have to identify them. We have to add a list of suspicious words that the model or the program can search for them in each document. For example, look at this list right here. Okay, we have this list, suspicious terms, in this list. Okay, the first suspicious word is verify, and we have account, login, click, suspend, update, and password. Okay, we are going to count how many suspicious words we have in each email. Let's go and check together. Okay? So, for example, in the second, okay, in the second email, okay, so verify, okay, is verify exist in email number 2? Yes, let me clean. In email number 2, we can find the term verify right here. Okay, change the color. We can find the term verify right here. So till now, we have one suspicious word in email number 2. Okay, so do we have the account term in email number 2? Let's search account is here it is. So till now we have verify and account. So till now we have 2 suspicious words in email number 2. Do we have login? Let's search and see. Yes, we have login. So this is the third suspicious word. Suspend. Okay, update to password. Update. There is no update right here. Is that right? Yes. And there is no password right here. Can you detect the word password? There is no password right here. So there is 4 terms: verify, account, login, okay, and suspend, which is right here also. Not suspend. We have also click. Okay, where is click? We can find suspicious. An account will be suspended. Okay, we have suspend. Okay, so we have verify, account, login, and suspend. We have 4 terms. Okay, 4 suspicious words. So how many suspicious words we have in email number 2? We have 4 suspicious words. Okay, and we can just count the number of suspicious words also in email number 1. We have 0 of them. And how many words we have in email number 1? 24 words. How many words we have in email number 2? We have 39 words. Number of characters in each email. And if the first email contains HTML, we will write right here 1. And the same applied for email number 2. And as you can see, the emails are in plain text. So because they are a plain text or in the form of plain text, of course there is no HTML, so the value here is 0. Okay, I hope that everything is clear. Let me clean everything. Okay, so after getting all the requirements that we need or that we are searching for, now we are going to concatenate the TF-IDF of email 1 and the values of the special features also of email number 1. Okay, like what's the TF-IDF of email number 1? Okay, let's write them. Let me put text right here. Put them in a list. The first row in TF-IDF email number 1 is 0.0111. So we will write 0.0111. The second one is also 0.0111. So come on, 0.0111. The third one is also 0.0111. The third, the number 4, okay, the row number 4 value is 0. Number 5 is 0. Number 6 is 0, and so on. Okay, and after adding all of the values of TF-IDF email 1, okay, we are going also to add to them the values of the special features of email number 1, suspicious words, number of characters, and has HTML. Okay, the first one of email number 1, okay, email number 1. The number of links in email number 1 is 0, so we will add to this list 0. Okay, as you can see. Just a second. So we will add to this list 0. What's next? The number of suspicious words in email number 1 is also 0. So we will also add 0 right here. The number of words in email number 1 is 24 words. So we will add 24. The number of characters is 163 and the has HTML value is 0. Okay? So after concatenating the TF-IDF with the special features, we will form a vector that we are going to use it in order to train our model later. Okay? So this is the vector of TF-IDF, or of the it's the final vector, okay, of email number 1. In the same steps, we can calculate the vector of email number 2. We can add these values and adding to them the values of these special features. Okay? We can find the values right here. Just give me a second. Okay, so right here we can find the final vectors. This is the vector of email number 1. And this is the vector of email number 2. Okay? So, these vectors, we are going to use them in order to train our model and to test it. So, this is all the project. Okay? I will go to the code right now and explain the code. Okay? So, first of all, as I said recently, we have to import some libraries like pandas, like TF-IDF factorizer, which just contains the TF-IDF that we calculated right here, and it will convert it to a vector like this one that we are going to use it in training procedure. Okay, and train test split, which will split the data we have into 2 data sets. The first one for testing purposes, and then the second one go to training, okay, and so on. And we are going to use the, as you can see right here, we are going, okay, just that, okay, we are going to use the model multinomial NB, which contains the tree model. I will explain it in a second, okay. Forest classifier is the name of the model. So first of all, we will upload our data to memory. I downloaded, as I recently said, I downloaded this data from Kaggle and put it on the same folder as the project with the name emails of CSV. So we will upload this data, okay, to memory by using the pandas library, or pandas library. Okay, we saved it in DF, stands for document, or sorry, data frame. Okay, then we have to make sure that there is no null values. So the subject, okay, is the same subject, but if the value is null, just replace it with empty string. And the same right here, the body is the same value, but if the value is null, replace it with an empty string. After cleaning the data, now we are going to concatenate the subject and the body after making sure that there is no null values. Okay, so we added a new column or a new feature named full email, which is the subject concatenated with the body. Okay, after this one, we are going to count the number of URLs in the email that we have. As you can see right here, okay, in the special features, we have a special feature called the number of links. So we are going to calculate it in the code. So the number of URLs in the email that we have is the full email, okay, and count the number of HTTP in that email. And that's the value of the number of links. After that, we are going to count the suspicious words or the suspicious suspicious keywords that we have. We create this list that composed of some suspicious words like verify, account, login, click, suspend, update, and password. And we set to the program that, look, just go to the full email and apply this lambda function to this email. So X is the email that we have. Okay, so count or sum of the number of words that we have in this email in which this word is found in the suspicious terms list. Okay, so the program are going to go over each word in the email, and if the word existed in the suspicious terms list, the value will be incremented by 1. Okay, after all of these steps, the value of this feature is the number of suspicious keywords that we have in the email. Then we are going to count the number of words and characters. It's the most easiest thing that we can do. Just apply the lambda function into this email X and count the email after splitting it based on the space. So the string are going to be converted to a list and count the number of terms that we have in that list. That is the number of words. Okay. After that, just also calculate the number of characters. Be a full name, but apply len, which will calculate the number of characters in that email. Now we are going to check if that email contains an HTML tags. Okay, how we can calculate that? So the value of this feature, the value of this special feature, is the full email. Okay, apply to this lambda function. The email is X. Now look at this regular expression right here. Okay, this regular expression re.search is applied to email X, as you can see. Okay, it's applied to email X, and here is the regular expression that we wrote. R, the small r, is to just use the backslash as a normal character, not as a special one, to avoid writing, for example, double backslashes like this one. Okay. So the regular expression is open arrow bracket, dot means any character, any number of characters that we have, but stop at the first close arrow bracket. And if this regular expression can find a similar shape in the email, so the has HTML will be 1. The value of it will be 1. So after that, we are going to calculate the TF-IDF text vectorization. Okay? Single words like account, click, login are unigram. Okay? Okay, it's a very important thing that I have to talk about. We have unigrams and bigrams. As you can see right here in the whiteboard, I added just the unigrams, which composed of only one word. Like meeting, it's one word. Reminder, one word. Reschedule, one word, and so on. But we can, for example, take two words together, like action required. Take it and put it in this table on the same row. Okay? Take action. We can write it right here. Okay, together. So it's not one word, it's two words. Okay? So this is the bigrams. Two words like login to, like click here, like your account. So now we are going to create an instance from the TF-IDF vectorizer. Okay? So the stop words, okay, which are in English, the program will ignore them, okay? And if the word exists more than 70% of the email, we can also ignore it. And this anagrams range is that we can use the unigram and the bigram. So this instance, which is the vectorizer, we are going to just convert the full email that we have into something similar to this. Okay, as you can see right here, okay, sorry, let me just move up. Okay, and clean this a bit. So if I just add a parenthesis around this table, I just wrap it up with a parenthesis, I can see that we can just look at it as a matrix. Is that right? And this is how the model can understand the values, okay? By converting them to numbers, and then a matrix, and after that converting them to vectors. So right here, we are going to transform the full email into a matrix, okay? And then into a vector, okay? And then here is the extra features. The extra features is the number of links, specious words, number of words, number of characters, and the has HTML values. We will add them to the same list and convert this list to be a NumPy list. Why? In order to concatenate it, as we recently see right here, we just concatenate the TF-IDF of the first email right here with the values of the special features of the same email, this email number 1 right here. We concatenated them together. So to do that, we have to convert the list of the special words into a NumPy array, and then concatenating it with the TF-IDF matrix. Okay, so TF-IDF matrix, which is the full email, okay, and then adding to it the extra features, will form the same shape as we have right here. Okay. As you can see, is everything clear? I hope that. So this is X, is the vector that we are going to train our model on, and Y is the label. Do you remember the labels? The labels is what identify whether the email is phishing or not. So let's now moving on. Now, as we said recently, we have to split our data into 2 chunks. The first set or data set for training, and the next one for testing. Okay, so xtrain, okay, is the number of vectors that we are going to use them to train our model. The xtest is the rest of the vectors that we left them in order to test our model later on. The same applied for ytrain, okay? The same number of vectors that we took right here, we are going to take the same number of labels, okay? But respectively the same emails, okay? So, and also the y-test. How we can split? The train test split function, okay? We will give it the vectors that we have and the label that we have, and the test size is 20% of our data, and this is like a seed to avoid the just scrambling within the data itself. So after splitting the data, we are going to train our model. But what's our model? Our model is the random forest classifier. This is a model, okay, that use many or numerous amount of trees. Okay, each tree has its own conditions, and based on these conditions, it just concluded whether the email is phishing or not. For example, if we have 100, let's take an example right here. If we have 100 emails, okay, if we have 100 emails, if we have 100 trees, like here, the number of trees that we have is the unestimators. We have 100 trees. If we have 100 trees, okay, we can just, based on them, for example, if 83 of them just say that this email is a phishing email, okay, so 80 is more than 20. So in conclusion, we can say that this email is a phishing email. After that, we can just fit or train our model, which is the model right here. Model.fit means train it on this vectors, which is the x-plane, and this is the respective labels of each vector, which is the y-plane. Okay, and based on these vectors and the predictions, based on these vectors that we train our model on, we can now start giving our model some vectors, try to predict them or predict whether they are phishing or not. Okay, so Y-pred is the model that we have that predict X-test. Okay, X-test is the rest vectors that we left in order to test our model on. So we are going to give them to the model, and the model will predict their labels, and based on the result, which is Y-pred, okay, we are going to calculate the accuracy, okay, evaluate the model. The accuracy of this model we are going to calculate it. We can compare between the Y test and the Y predicted from the model, okay. So this Y test is the correct labels, and this Y-pred is the labels that the model predicted, okay. So we calculate the accuracy, the confusion matrix, the classification report, and then after that we trained our model, we tested it, and now let's write our own email. The email is alert. Your email account is being deactivated. Click here to cancel the process on this link. Okay. So we are going to redo the same steps. We are going to just take the email because we need it as a string, not as a list. So a new email 0 will take this string from this list. Okay. Then we are going to count how many links that we have. We put it in a list in order to concatenating or in order to concatenate it with the other features later. Okay, so this is the number of links in that email, the number of suspicious words that we have in that email, the number of words, the number of characters, and if it has an HTML tag or not. Okay, so after that we are going to just factorize it, but transform a new email. What is the new email? This is the new email. We are going to convert it to a matrix, okay, new email vector. So now the new features, here is the new features. We calculated it recently. The number of links, number of suspicious words, number of words, number of characters, and if it has an HTML tag or not. Okay, so these features we are going to concatenate or to concatenate them together to form only one numpy list. So np.array, new email links, new email suspicious, which is the number of suspicious keywords that we have, new email words, new email characters, and so on, the new email HTML. So after that, new email final, we are going to concatenate both the features and the vector that we take from the new email. Okay, so H stack, new email vector, new features. Okay, then we are going to give this new email final to our model, and the model are going to try to predict the label of this email. Okay, so after the prediction procedure, this variable can hold one of the two values, either 1 or 0. Okay? So the new email prediction is phishing if the prediction is 1, and else means that if the prediction is 0, else then it's a legitimate email. So that's all what I have to say in this project. I hope that you found it useful and important to you. So is there any question or is there anything that anyone need to ask about? حسن بعدك معي؟ حسن؟ اوكي. حسن ناخذ بريك نقصر منطر شوي. إذا في أسئلة، إذا في شي بحب ينسأل. يا هلا أمينة يا هلا. So إذا في شي أسئلة, if there is any question that you would like to ask and to re-explain it from scratch, just ask, okay? Thank you very much. You are welcome, Rihana. So that's all for today. Thank you for your attending. Okay, okay, okay.